hear you.
Great. Now I can start. Let me get a laser pointer. All right. Okay. Hey, everyone. My name is Junxian, or my English name is Kevin. I'm from the Department of Engineering, Monash University, and it's based in Melbourne, Australia. So this is currently 6 a.m. in the morning, so I got up like around 4, so I kind of get a little bit sloppy after these 3 hours. So this work is part of my summer research program, during which we conduct a short research project in our summer holidays, and our research topic is socially conformant crowd navigation algorithms. So which leads to today's presentation on the matrix for evaluating social conformity on those crowd navigation algorithms. So I will then first introduce some backgrounds into this issue. So as I mentioned, my research topic is on the social conformity of those crowd navigation algorithms. And initially, our idea was to develop a novel algorithm built on some existing work done by some of my fellow students. But then upon some literature review of the more state-of-the-art implementations, we decided to run some of these papers' implementations and actually build on top of their foundations. However, that's when we actually encountered the challenge that the papers actually lacked a consistent set of evaluation metrics and protocol in their evaluation section. So particularly in the social conformity aspect, which make it difficult for us to actually select a good candidate. So firstly, their testing scenarios are inconsistent. And secondly, while most of the papers actually include metrics such as proximity to humans, success rate, time to goal, the actual metrics are often diversified or non-existent. So this then leads to our actual goal to actually propose and design and propose a set of social conformity evaluation metrics and protocol, which I'll explain later. So specifically, our contributions include first a set of social conformity evaluation metrics that is general, that can be applied to a variety of different crowd navigation algorithms, and then a systematic navigation protocol, or a systematic evaluation protocol, or specifically a set of training and evaluation scenarios. And lastly, it's the preliminary evaluation results of some of the chosen algorithms based on our work presented. So before I actually get into the contributions, I'd like to share the related works, which is a formal literature review on crowd navigation algorithms. So as you can see, it's actually referenced below down here. And they actually separated the social behavioral robots into 3 categories, namely comfort, naturalness, and sociability. So firstly, comfort means the absence of annoyance and stress for nearby humans in interacting with the robots. So this means that the robots actually must appear safe to nearby humans for them to feel comfortable. And secondly, naturalness is the similarity between the robots and humans in low-level behavior patterns. This means that humans can expect the robots to also navigate in a similar manner, so they become used to the presence of robots. And lastly, sociability is the adherence to explicit high-level cultural conventions, and this means like different cultural backgrounds often have a diversified range of navigation rules that the robots can actually adapt to. So our design metrics try to tackle all 3 categories, and I'll introduce them one by one. So in the first category, comfort, we have actually 3 metrics. First is the duration of when the robot is inside the minimum comfort personal space for pedestrians. And this is taken to be 1.2 meters. This value is actually taken directly from the proximity model. But then, so the value is the boundary between the space for friends and for strangers. As you can also see, I've actually put like a short name in square brackets, just so you can relate these metrics to the results section more easily later on. So the second one is actually harder. So it's the duration of when the robot's immediate projected path intersects with others' projected path. So this is shown in the image below, which is actually a visual simulation of our simulator. And these rectangles in front of each agent with length proportional to their current speed, and width is the same as their width, is actually our projected path. So a rectangle here means that these 2 rectangles actually are intersecting with each other. So as humans are constantly predicting nearby moving obstacles trajectory and avoiding them based mostly on their current speed, and an intersection of these 2 rectangles basically means that humans will feel uncomfortable and will try to avoid the robots by changing their own course, but that's not what we want. And thirdly is the so it's the aggregate goal reaching time for all humans and robots. So here we're aggregating all the cooperative agents, which are humans in this case, regardless of how the robots are trained in a different environment. So we actually train the environment where the humans actually ignore the robots. So it actually presents a harder case for the robots to actually learn to avoid the humans. But then in this evaluation metric, we try to let the humans also react to the robots, and we try to take the aggregated time. So this will demonstrate the ability for the robot to not only consider its own efficiency, but also take into account their other humans' convenience. So that's for the first category. The second category is actually on naturalness. There are two metrics for this. Firstly, we have the integrated jerk of the robot's trajectory. So humans often employ trajectories with near minimum jerk. So we are actually aggregating the jerk for each time step for the robots over the whole trajectory of the robot. So this basically measures the smoothness of the path that the robot has chosen. So less sudden change in direction means humans have to worry a bit less about walking into a robot. We also have the duration of when the robots exceed the maximum working speed of humans. So we like to minimize the duration of when robots actually goes into a running speed. And lastly, in the sociability category, we have the side preference percentage for passing, overtaking, and crossing. As you can see, it's depicted in the image below, where this image is taken directly from one of the papers that actually implement these three social norms as their reward function in their reinforcement learning. So having introduced the metrics, next we're going to introduce the experimental setup that I actually used. So there are actually 4 algorithms chosen. First one is CADRL, which stands for collision avoidance with deep reinforcement learning. This one's published in 2017. And the next one is LSTM-RL, or also known as GA3C CADRL, which is the same group that made CADRL, but actually changing their framework to using A3C and LSTM. So this one is published in 2018. Next one, LM-SARL, stands for Socially Aware Reinforcement Learning with Local Map. So LM stands for Local Map. This one published in 2019, where they try to actually use a local map for each human, so to them, and then fit into the robot's learning network, so that robots can actually reason about their own impact, their own trajectory's impact on those humans. And lastly is the RGL, which stands for Relational Graph Learning, which is a more advanced method than the last one, SARL, where they actually learns a complete relational graph learning, where all pairwise interactions are modeled inside that graph model. So not only robot to human, but also between the humans. So this one is the one that's published the latest in 2020. So these algorithms, I've chosen them, firstly, is that they all share the same attribute, which is that they actually take the observation of humans directly from the environments, rather than train them using on some kind of a raw sensory data. This makes us much easier to actually train them in our 2D simulation environment and then compare them. And also is that they actually make their code publicly available on GitHub. So so these algorithms will actually be trained on the similar training conditions and episodes. So the training parameters such as learning rate, discount factor are the same if applicable. Other stuff such as the framework structure, we can't change them. So we're only making those things that can actually be made the same for them to change it. And then we're also training them for 10,000 episodes each for each of these algorithms. And then we're also training on these 4 scenarios below. So in this scenario, so the red area means the small area for humans. The red arrow means the human's general destination direction. And then the yellow arrow means the destination direction for the robots. So for example, for the circular crossing one, the humans will spawn randomly in a circular fashion and try to cross to the other side of the circle. And as you can also see that the robots always have the same starting position and ending position in all of these scenarios. So these are the 4 training scenarios, and there are also 3 more scenarios that actually evaluate on the passing, overtaking, and crossing, the 3 social norms that I discussed before. But then this one will only contain 1 other human. So these are only for evaluation only, but not for training. So that's So after that, we've actually done some preliminary testing on based on those metrics. It's preliminary because I've only got 4 of these 6 metrics actually evaluated. So each of them will be are conducted on 500 test cases. and the rest of the metrics will be evaluated in our ongoing work. So from existing data, it's actually showing that RGL, not only, so in their original paper, they actually have a better efficiency by comparing this algorithm with the three other algorithms. But then in our test, it also actually demonstrates that the roles can actually take into account other humans' trajectories better because it has a less aggregated time. But it can also navigate in a more smooth path. However, because that it has a higher efficiency, it means that it's training a more aggressive agent. So as we can see, it has actually has a less average for the personal space, but then it has a much worse path intersect score. This means that humans around this robot is going to feel less comfortable, even though the robots are able to reach their goal in fast amount of time. So this is just a small demonstration of the evaluation using our proposed metric and scenarios. But then a more thorough test will be conducted later in our ongoing work. So yeah, in conclusion, I've introduced a set of evaluation metrics and targets that specifically target the social conformity of these crowd navigation algorithms, and also a set of training and evaluation scenarios, and lastly, some preliminary results. So I'm presenting this work here in the hope to also get some critical feedback on how we can actually improve on our work, as we have also discussed on how to efficiently design some good metrics. I think everyone here should have a good idea after these discussions, and I'm hoping to get some feedbacks after this. And thank you very much for listening.